Thank you for waiting. Projected impact of climate change on world food supply and demand using the Impact World Food Model, a Senior Research Fellow, IFPRI Dr. Keith Wiebe.
Thank you very much. Thank you to JIRCAS for hosting us today, for the Ministry of Agriculture, Forestry and Fisheries for supporting this work and this discussion on this very important topic. Also, thank you to the previous speakers who have very nicely set up some of the points that I will talk about now. Some of you may have participated in the seminar hosted by MAFF yesterday. You will recognize some of the slides that I shared today, but I will add much more of a dimension focusing on the impacts of climate change. And again, thank you to the previous speakers. They've helped introduce some of the points that I'll be talking about here. First of all, let me also just mention that this work draws on the contributions of many colleagues at IFPRI, and I'd like to acknowledge their contribution as well. Okay, I'll talk today about several aspects of this problem, starting with challenges facing the world's food system, looking more particularly at climate and other major drivers of change in the system, how we approach analyzing these questions using the impact model at IFPRI. Then I'll turn to some of our recent projections, and I thank Mr. Koyama for making the distinction between projections and predictions. I'll talk about that a little bit later as well, and then draw some conclusions. So I think you all are well aware that while we often think primarily about agriculture and production, including when we talk about climate change, there are many other aspects of food systems that are also critically interrelated, and all of them also are influenced by climate change in different ways. I will today talk mostly about production, resources, and consumption aspects, while acknowledging the importance of policy and investment to influence those pathways, and also noting impacts on other parts of food systems, transportation, infrastructure, processing, and so forth, even though I won't spend too much time on those today. Now, the previous speaker, Dr. Meyer, thank you for talking about some of the recent trends over the past half century that have brought us to where we are today. And I'll just repeat some of those very tremendous challenges and achievements that have been overcome, including a major concern a half a century ago, which was population growth and how do we feed the world's growing population. In the slide that you showed that world agricultural and food production has actually increased more rapidly than population over the past century. So that's one achievement. That doesn't answer all of our problems, but it's a very major accomplishment. Nevertheless, we're left with many other kinds of challenges that face us today. Climate change is a critical one of those and the focus of our discussion this afternoon. But we can't look at climate change into the future without recognizing other things which also confront the food system. That includes population changes, growth in some areas, declines in other areas, and those each have their own particular challenges associated with them. Changes in demand, depletion and degradation of natural resources, food loss and waste, different aspects of malnutrition, undernutrition, overnutrition, micronutrient deficiency, and so forth. I note here, because Seth mentioned the ghost of Christmas past and the ghost of Christmas present, behavior is really a part of both the challenge and our opportunities going forward. We don't necessarily make bad choices on purpose, but collectively our individual choices can have negative impacts on the world food system. Nevertheless, that also presents an opportunity going forward to make changes that can improve future outcomes in the directions that we would like to see. And those opportunities take many forms, including things like improvements in information access and technology, economic growth, opportunities for improved investment, better policies, and of course, improved behavior as well. So let me talk a little bit more about drivers of change. I'll start with drivers on the demand side and then turn to drivers of change on the supply side, which includes climate change. Now, these have also been noted by previous speakers. I won't need to elaborate much, but just to note that in many parts of the world, population growth remains a challenge. You can see here In the middle of the graph on the left, that sub-Saharan Africa's population continues to rise and is projected to continue rising through the remainder of this century, whereas in other regions, this region where we are today, East and Southeast Asia, populations are leveling off and beginning to decline in some cases. Same is true in other parts of the world. So there are different experiences in different regions of the world. Each of those has its own implications for changes in demand in the future decades. Along with changes in population, also changes in income. While these certainly experience fluctuations and shocks, the projections over the long term are that they will continue to rise in all parts of the world. Although starting from very different levels, you can see very low growth points for both sub-Saharan Africa and South Asia, but actually quite steady projected increases in income in those regions. Growth as well in other regions of the world, but starting at higher points and therefore at slower rates incrementally. The combination of those, faster income growth and combined with population growth in many regions, those are the real sources of increase in demand that we see. And it's not just demand in aggregate, but a change in the composition of demand as well. So we also observe over time that populations are moving increasingly to urban areas. Today, just over half of the world's population live in urban areas, and that ratio continues to increase. And the combination of these factors, urbanization, income growth, globalization, these all combine to influence changes in what people choose to eat. And very broadly, to summarize what's actually a very complex process, we see a transition from basic staples to more fruits and vegetables, to more animal products, to more processed foods. And those have different implications for health and nutrition. Many of them positive, some of them also adverse health impacts that we need to be aware of. On the supply side, I can go through this one fairly quickly because Seth showed you a similar graph. This one, his was a bit more updated. He has the most recent decade in there, which shows a downturn. But basically, just to reiterate, this shows that the majority of growth, especially in recent decades, growth in agricultural output, comes from doing things better, being more efficient in how we use land and other inputs. And so that, in turn, is a reflection of improvements in skill, information, precision in how we apply inputs and so forth. So there's tremendous gains there. Seth noted that that has slowed down in recent years. There are also quite significant differences across regions. Some parts of the world, particularly sub-Saharan Africa, lag this global trend by several decades. And they continue to see much more of their output growth coming from increases in area and in input use as opposed to inputs in efficiency and TFP. So now we turn to climate. Climate has been changing for as long as the world has been around. This graph I like because it goes back 20,000 years. It gives us a bit of a longer-term historical perspective. But you could see even more variation in climate if you went back 100,000 years or 1,000,000 years or 100 million years. That's the experience of world history. What's really interesting to me are two factors. One is the entire history of agriculture itself, that's the domestication of crops and livestock, has taken place over the past 10,000 years in a period of relatively stable temperatures. That's, as I said, domestication of crops and animals. It's settlement in villages and then towns and cities. It's the development of writing, trade, all the things that we consider as culture, not just agriculture, but culture itself have taken place in a period of relatively stable temperatures. We're now at a turning point that we've been experiencing in the past century or so. And this is clearly highlighted in the work of the IPCC as well, as Dr. Hasegawa introduced just a little while ago. And that brings us to some real challenges in terms of what impact that will have, not just on agricultural production, but other aspects of the food system as well. So we're now at a point in roughly the middle of this graph in 2024, where we're just on the threshold of about 1.5 degrees Celsius warming relative to the Industrial Revolution about 150 years ago. Where temperatures go in the future, that's uncertain. It's uncertain because climate systems are very complex, and it's uncertain because they depend also on the choices that we make today and in the coming years, individually and also collectively as society. Here's where we make a distinction between predictions. We're not in a position to predict which exact pathway we'll be on, but we can make projections of what would be the implications if we're on a high climate change pathway as opposed to a low climate change pathway. And that's the focus of some of the results that I'll show you in a few minutes. We will look at what we consider our baseline scenario, which assumes climate change at the level considered high here, RCP, or Representative Concentration Pathway 7.0. And I'll also compare how the impacts of that pathway compare to what would happen if we were on a lower emissions pathway, RCP 2.6. So we often think about climate change as a long-term, sometimes distant in the future challenge. But in fact, we experience it already today. And we see it in many parts of the world. In the news recently, we've experienced severe hurricanes and major flooding damage in the United States. We've seen that recently in Spain, in the Philippines, other parts of the world. We've done some work at IFPRI that looks at the increasing frequency of particular, in this case, drought events in southern Africa. And this is work done with the Massachusetts Institute of Technology, MIT, where they've run thousands of different climate scenarios to look at the frequency of, in this case, drought events that are significant enough to significantly reduce maize yields in southern Africa. And they just illustrated here 4 scenarios. On the upper left, basically where we are today, 1.5 degrees Celsius over pre-industrial levels. What the different shades show is the frequency with which a drought of a certain magnitude would occur. And you see here in the first graph, in most areas, the color shaded indicates blue, green, or a little bit of yellow. Those indicates that such drought events could be expected to occur maybe every 20, 25, even 30 years. But it varies a little bit by different locations. As the rate of temperature increases, in the upper right figure, you see a lot more yellow. That's where this drought is occurring or projected to occur maybe once in 15 years. In the most extreme scenario in the lower right, you can see that in many parts of southern Africa, that severity of drought is now projected, or would be projected to occur under a more rapid climate change scenario, as much as frequently as once every 5 years. So you see a very sharp increase in this occurrence of drought events that are fundamentally important, not just to producers of maize and other food crops, but to consumers in the whole region as well. This is just an example from southern Africa, but one might expect similar types of trends to be seen as well. So extreme events is often the most immediate and most direct kind of realization of climate change that many people experience today. But it's not the only one. We can also anticipate longer-term impacts on agriculture and on food systems more generally. Now, analyzing those longer-term impacts requires us to make assumptions, as the previous speakers have noted. We can look at different emissions pathways and look at scenarios in which emissions grow very rapidly and temperatures rise accordingly, or more optimistic scenarios in which emissions grow less rapidly and, as a result, likewise, global and local temperature changes as well. Each of those has their own pathways and implications for yields of crops. So one step in analyzing the impacts of climate on agricultural production is to look, first of all, in biophysical terms, how will changes in temperature, precipitation, various other measures, solar radiation, so forth, how do those actually affect crop growth? And that's the starting point to see then how might those impacts trace through the economic system. This is work published a couple of years ago, not by IFPRI, but by colleagues working in the Global Gridded Crop Model Intercomparison Project. And that's a number of different crop modeling groups around the world. In this case, excuse me, they compare results for maize on the left and wheat on the right, just to highlight the very different experiences that different crops may experience with changes in temperature and also different regions. And this is really, you can see a really sharp difference. Without going into the details here, maize is much more sensitive to increasing temperatures. And you can see in the lower left, the red areas very widespread around the world with potentially significant reductions in maize yields as a result of higher temperature. These are higher temperatures as well as changes in precipitation. On the right, by contrast, you see the projections for wheat. Quite a different experience. Wheat is grown typically in different areas today, typically more temperate, cooler, and a bit more tolerant of increases in temperature. So as a result, both of where it's produced and the physiology of the crop itself, it tends to be much less sensitive to increases in global temperatures, and in fact, benefits in terms of increased yields in many regions as well. So just to highlight that there are very different experiences by region, by crop, and not included here, also differences in management practices. And that brings in the interesting dimension of the different resilience ability of wealthier farmers who can afford adjustments in farm management practices, input levels, and so forth, with farmers who have much less capacity or wealth or resources to change the way they farm and produce different crops. Now, important to note here, these are changes that would be expected with changes in precipitation and temperature and possibly other biophysical dimensions, but they don't account for adjustments, whether it's in farmer management practices, whether it's investment in R&D that develops new varieties and so forth. And this is very good as a scientific experiment. You want to isolate the impacts of climate change. You hold everything else constant. It's only an intermediate step when you're thinking about a policy analysis, because a policy analysis, you want to also account for other things that are changing. And that recognizes that as conditions change, farmers are very likely to adjust their planting dates. They might adjust how much water they apply. They might adjust which varieties they plant. They might adjust where they plant different crops. They might even adjust the crop mixes that they do and switch from one crop to maybe one that's less sensitive to changes in climate. So all kinds of adaptations need to take place, and that means that this is an intermediate step in the analysis, but we want to bring in then the economic modeling as well. And IFPRI's impact model is one of those tools. It's not the only one. There are other modeling groups around the world, including here in Japan. We'll hear more this afternoon from the JIRCAS analysis. There's also a group that uses the AIM model here in Japan. We collaborate with them as well as with other partners in Europe, in North America, and around the world. What they have in common, broadly speaking, is they take inputs from climate models, typically changes in temperature and precipitation, but also some other variables. They use climate models and sometimes water models, as in the case of impact, to see how those things are going to change with climate. And then we introduce human behavior. How will farmers respond? How will consumers respond? How will markets respond? And then how do those in turn interact to generate the final sorts of impacts? I won't go into this in detail because we have limited time today, but impact brings those different elements together. We don't do the climate modeling, but we take the inputs from others who do. We do crop modeling, we do water modeling, we do economic modeling. Those different tools interact, both in terms of the global agriculture sector, and then we work with the globe general equilibrium model, which brings in interactions with other parts of the economy as well. Impact is relatively disaggregated, both geographically. We have about 160 countries where we do the economic analysis. Within countries at the pixel level, we do the water and the crop modeling at a higher resolution. We also have quite a high level of disaggregation by commodity groups, and just very briefly, that includes animal source foods, cereals, fruits and vegetables, oil crops, commercial crops, pulses, roots and tubers, sugar crops, and a few others as well. So how do we bring these together? This corresponds basically to what I was talking about a little bit earlier. We have changes in temperature and precipitation and some other variables that come from climate models. And we can draw from different climate models. We happen to use the IPSL for our baseline scenario, but we also look at other crop model or other climate models as well. We can choose which emissions pathway that we're going to focus on. The results I'll present today are largely with RCP 7.0, but then comparing a lower emissions pathway, RCP 2.6. We look to a horizon of 2050. Some models go farther in the future. We'll hear later this afternoon about the JIRCAS model, which goes to 2060. Others go to 2080 or even 2100. But that then generates this intermediate step in the analysis. That's the crop model results that look at what happens to crops, which we grow today, where we grow them today, how we grow them today, holding other factors constant. But that's, as I mentioned, that's an important intermediate step. We do that in this example. It's done for maize using the DSTAT crop model. But it's really important to figure out then how will consumers, producers, and others respond? How will markets respond? Price changes, and what does that induce? And that, in turn, results in an adjustment to our final estimate of what happens to crop production and other food-related metrics. So this is another graph that's similar to one that Seth showed just a few minutes ago. And I won't go into detail. I just wanted to show you some broad trends that we typically see in our analyses. This particular study, this is about 10 years ago, and it brought together about 10 different global economic models, not just impact. And it looked at multiple crops in multiple regions, so there are many different results that are summarized here. But basically, what we can expect to see in this type of analysis is that before adaptation, you see yields declining by a certain amount. When you factor in adaptation by farmers and consumers, you tend to see there is still a yield reduction for most crops. In some cases there's a gain, but in most crops there's a reduction. But it's less so than it was before the adaptation. The second important thing is total consumption does change a bit, but probably less than you might expect. Demand is such an important driver. Populations continue to grow, incomes continue to grow, people need to eat. That demand is not going to change just because the temperature got warmer. What does change, since yields have gone down, is that area needs to expand to compensate, and prices need to expand, need to increase. And those are really important dimensions. They're part of the response, but they introduce their own challenges. Area increases means that land is being switched, sometimes from natural uses, sometimes from other types of land cover, often with environmental impacts that we need to be concerned about. Higher prices, obviously also. They are good for some producers if those increases are not outweighed by increases in the price of inputs, but they also make it harder for consumers, particularly poor consumers, to access the food that they need. So this is just a general kind of summary of a tremendous amount of different analysis that goes into this sort of thing. Now, to distinguish projections from predictions, our first two speakers this afternoon emphasized the importance of making clear the assumptions. These aren't all of the assumptions that we bring into our models, but these are some of the critical ones. We take the work that I'll present today, population and income trends from the IPCC medium pathway, shared socioeconomic pathway 2. We make similar sorts of adjustments in productivity growth. We look at RCP climate, or RCP 7.0, and then to compare, we also look at RCP 2.6. And later, I'll very briefly talk about some alternative investment scenarios. So getting on to our results. How am I doing on time? Okay. A very general summary. Population continues to grow between 2010 and 2050. The IPCC SSP2 projections are that world population grows by about 35%. But because incomes are also growing, demand for different types of food also increases more rapidly than population, but at different rates for different types of food groups. At about 50% over that 4-decade period for cereals, more rapidly for animal source foods and for fruits and vegetables. Those are higher value products that become more appealing to consumers as their incomes rise. This is a detailed graph. I'm not going to go into it in too much detail in the interest of time. It just shows that it's not just production that is affected by climate change, but climate change also traces through to changes in what kinds of food are available for people. In the first bar for each region, these are figures for different regions of the world, and they're defined at the bottom of the graph here. In general, you see that availability of different types of food increases for most food groups between 2020 and 2050 in our baseline scenario. It would increase even more in a low climate change scenario. Just because yields are reduced less, prices grow less, more food is available, demand is also allowed to increase a little bit more. I'll note that there's relatively little change in cereals. There's more rapid change in fruits, vegetables, animal source foods, oils, and sugars as well. But I won't go into that detail. Just to show now here, the next graphs here specifically compare rates of change in what's labeled here as a business as usual scenario. It should simply say RCP 7.0. So more rapid climate change in the black, and then the green line in each case shows what it would look like in a lower emissions pathway, RCP 2.6. And if you look at Southeast Asia, for example, demand increases by, about 200 million metric tons of cereals between 2020 and 2050 under the higher emissions pathway. It would increase even more under a low emissions pathway. That's because production wouldn't be reduced by climate change. Prices wouldn't be as high. There would be more demand and more production responding to that. Similar pattern in other parts of the world. That's related, as I just alluded to, by differences in how prices change. Prices rise more rapidly with higher climate change. They would continue to rise for most commodity groups, but at a lower rate if climate change was also occurring at a lower rate. So a very general pattern that applies in slightly different ways across different commodity groups. Sources of growth. This also echoes what some of the previous speakers have talked about. Yields continue to rise. That's because climate change isn't the only factor at play over several decades. We see innovation, we see productivity growth. Some of that is coming from increased input use, some of it is coming from total factor productivity growth, just improvements in how smart we are in producing. So yields grow, but area also is contributing at different extents in different areas. In Eastern Southern Africa, in West and Central Africa, in Latin America and the Caribbean, area expansion continues to be a significant source of productivity growth. It's hard to see in this graph, but with higher climate change, a slightly bigger share of that output increase typically comes from area. And that reflects the pattern I mentioned earlier. Yields tend to go down as a result of climate change or grow less rapidly, and area has to pick up some of the slack. So different rates of growth in cereal yields in different regions, but again, you see they would be higher, they would be more rapid with lower climate change. This is a very broad aggregate. We put in here both maize and wheat, which you saw in an earlier slide have quite different experiences with climate change. But for cereals as a whole, this is a pattern. Production in most low and middle income regions, production lags demand growth, with the exception of Latin America. And you can see on the far right, the CG6, that's just our shorthand for low and middle income regions. As a whole, demand exceeds production. The opposite is true of the rest of the world, which is high income countries, including Japan, as well as the former Soviet Union. Those continue to be the major exporters that supply that shortfall in other regions. Similar story with some different features for rice. Here, both South Asia, Southeast, and East Asia see the opposite experience with production exceeding demand, and then those are sources of exports, as we'll see here. Largely, this is for cereals as a whole. Latin America and the Caribbean, rest of the world are the sources of exports for cereals that go to the other low and middle income regions. What you see in the light green, that's the lower climate scenario. Latin American exports would have risen even more rapidly, or would rise more rapidly under lower climate change, but that growth is curtailed a bit with more rapid climate change. In the case of rice, a similar story for South Asia. It continues, the projections are that it continues to export more rice, but it would have increased even more rapidly with less climate change. Risk of hunger, sorry about that. The risk of hunger, both population numbers as well as the share of population at risk of hunger, they decline in all regions under the scenarios that we're looking at, and that's because of the assumptions about income growth as well as improvements in technology. but they decline less rapidly. The progress is slowed the more rapidly that climate changes. Now, very briefly, I'm not going to say too much about alternative investment scenarios other than we have explored them. We've looked at the impacts of more investment in agricultural R&D, investments in land and water use that improve water use efficiency, investment in infrastructure, and I'm simply going to jump right to what those things could potentially do in terms of hunger. If you look at the left set of bars, the world set there, blue is where we are in terms of hunger today, or in 2010 in this case, over 800 million people in the world hungry. That would have dropped by half to the orange bar in the absence of climate change by 2050. Climate change reverses that progress. It adds another 100 million people globally who can't escape from hunger as a result of climate change, but investment has the potential to offset and more than offset those losses to climate change. Just to echo, and a similar pattern is seen in other parts of the world. Now, an important, almost final point here. This is work by colleagues Tomoko Hasegawa and others in Nature Climate Change several years ago, looking at potential impacts of climate change. They looked at RCP 6.0 and found that that has adverse impacts on availability of food and the incidence of hunger. But ironically, mitigation efforts, if that involves taking land out of food production and either keeping it in natural uses or diverting it to use of cropland to produce energy crops, then that in itself imposes challenges to food security. It doesn't say we must not look at those types of mitigation measures. It just means we need to be very conscious of what the different and sometimes unintended consequences can be, because sometimes they surprise us. So in conclusion, extreme climate events will occur more frequently. Longer-term impacts will vary significantly according to different crops and different regions. Importantly, changes in management practices as well as consumption behavior can have an important effect in moderating those climate impacts. Even with climate change, we expect that changes in population, income, diets, and technology will continue to be the major drivers of food system change for the next couple of decades. That won't necessarily be true after mid-century, but during our projection period to 2050, that's what we see. Prices will rise more rapidly because of climate change. Hunger will decline more slowly. Higher prices and area expansion can offset some of the impacts of climate change, but they come at their own cost that we have to be conscious of. I'll just jump ahead. Investments can help us offset these different challenges, but we have to be very careful about what some of the trade-offs are and some of the unintended consequences. I've indicated here some sources of more information. I hope these slides will be shared and you'll be able to look up if you'd like to follow up to find more details on that. But thank you very much for your interest and your attention.
Thank you very much for a very informative lecture. Thank you so much.